Okay, so let us start. Bismillah ar-Rahman ar-Rahim. In today's lecture 7, we will discuss about branching pipes, problems. Then we will discuss empirical equations for pipe flow and pipeline with pump or turbine. So we have branching pipes. In the last lecture, we discussed about pipes in series, pipes in parallel. So we continue in that fashion. The next topic is branching pipes. As you can see here that we have 3 pipes. They are connected clear to each other and the water is flowing through them and they are connecting 3 reservoirs. Clear? So branching in pipes occur when water is brought by pipes to a junction when more than 2 pipes meet. Clear? So you can see here that this J, it is the junction, the meeting of the 3 pipes. If we have 2 pipes, then it's not branching. Clear? More than 2 pipes they meet. Clear? So it can be 3 pipes, 4 pipes, and so on. So this system must simultaneously satisfy 2 basic conditions. What are the 2 basic conditions? The first one is that the continuity and energy equations require that the flow entering the junction equals the flow leaving it. So what will be the continuity and energy equations require? That at this point J, which is the junction point, the meeting point, the flow entering the junction equals the flow leaving it. So it means that whatever flow is coming to the junction point of these 3 pipes, the same quantity of water should leave that junction. Clear? Or in other words, summation of flows must be equal to 0. And this summation of J, this summation of Q at J, summation of discharges at the junction point. So this will be equal to inflows so we have inflows, water coming to the junction, minus outflows. And this must be equal to 0. This condition has to be satisfied. The second condition is that the pressure head at J, which is represented by imaginary open piezometer head tube with water at elevation P, is common to all pipes. This is important. It means that whatever is the pressure head at J given by this imaginary piezometer. So this is an imaginary piezometer. We want to represent the pressure head at the junction J. This is common to all pipes. This will be common to all pipes. Just like if you remember in the last lecture, we discussed about pipes in parallel. So the 3 pipes, they meet at A, clear, the entrance where the flow enters into the 3 pipes, and then they discharge again at some downward point B. If you remember, there was a point here in pipes in parallel that we discussed, and then there was one pipe, then there was another pipe, and then there was a third pipe, and then they meet again at some downward point B. And then at this point we have the piezometer, and then at this point we have the piezometer, and then the difference of level was represented by the head loss. So in a similar fashion, in this case, the pressure head at J, that will be common to all the pipes. Clear? So what we can say is that pressure at point J, that will be equal to P, and it is given or measured by this imaginary piezometer. Clear? If there are no pumps, the elevation of P must lie between the surface reservoirs A and C. So in this case, it is possible that we can have a pump. Clear? So what is the purpose of a pump? If you have studied, the purpose of the pump is that it aids the energy. It aids the energy to the flowing water. So then in that case, the water level can be raised. Clear? To the required head provided by the pump. But if there are no pumps, we are assuming in all these cases that there are no pumps connected. So then the elevation of P must be between the surface reservoir A and C. It means that P will always be between A and B reservoir surfaces. You can see here this is point P. So this is the surface reservoir elevation of A, and this is C. Clear? So P is always between the two if there are no pumps. So we will discuss different cases. So in all the cases, this elevation P, clear, this will be between the two, between the surface elevation of reservoir A and C. If P is level with the surface of reservoir B, clear, then H2 and Q2 are both 0. It means that if this is the reservoir B here and P is here at the same level, now this is P, clear? Now this is P. So then it says that in this case, what will happen, that H2 and Q2 are both 0. Then in that case, Q2 will be 0. This Q2, this will be 0 in that case. And H2, it will also be 0. So in that case, P and here, the elevation of the surface reservoir B, if they are level, then in that case H2 and Q2 will be 0. Clear? In the second case, if what we have, that P is above, it is above the surface reservoir B, then water must flow into B. Like in this case, you can see here P is above the reservoir B surface. So then in that case, what we have is that water will flow into reservoir B. Clear? And then the continuity equation at J will be equal to Q1 equal to Q2 plus Q3. Because this surface level is higher than P, so water will flow from reservoir A towards the junction point J. So that's why you can see that Q1 is out of reservoir A. And this is above B and C. So it means that water will flow into reservoir B and also into reservoir C. So then in that case, the continuity equation will be equal to that Q1, because this is inflow, so this will be equal to Q2 plus Q3, both are outflows. So what we see here, that this Q1, this is basically inflow. And this Q2 plus Q3, this is outflow. Clear? If P2 is below the surface reservoir B, then water flow must be out of B, and in that case it will be equal to Q1 plus Q2 equal to Q3. So when this P level is below, clear, the surface reservoir B, so you can see here, let's say it is here, this is now P. So then in this case, this will not be true, but flow will be out of reservoir B. This will be Q2 in that case. Clear? So Q1 will be the same. Q2 will be into the reservoir, out of the reservoir B into this junction point J, and Q3 will be into reservoir C. So then in that case, you can see that Q1 plus Q2 will be equal to Q3. So for the figure that is shown above, the governing conditions are for this case. Clear? For this case, which is shown here, so now in this case you can see that Q1 will be equal to Q2 plus Q3. Q1 is the outflow from reservoir A, and Q2 and Q3, they are inflows to the reservoir B and C respectively. So for this given figure, this is the equation that will come from the continuity, and elevation of P is common to all the three pipes. So this elevation P, it is common, clear, to all pipes 1. This is here pipe 1, and we have pipe 2, and we have pipe 3. So because it is the common meeting point, so that is why this elevation of P, it is common to all the three pipes. Now we have different cases. So if we consider case A, in this case now the situation is that EP is greater than E2, where EP is the elevation of the water surface, clear, at this point P here, at this point P. This is elevation of the point B in the piezometer above an arbitrary datum. So if we consider that EP is greater than E2, now this is A2. You can see here, this is A2. So in this case, what we will have, that Q1 will be equal to Q2 plus Q3. As we already discussed, if this is the situation, then Q1 will be equal to Q2 plus Q3. Now we apply the energy equation between the surface of reservoir A and point P. Now we apply energy equation between a point here and another point here, point P. So in that case, what we will have? We have P1 by gamma plus Z1 plus V1 square by 2G. At this point here, this is P1, clear? P1 by gamma here, V1 square by 2G plus Z1. And this will be equal to PP by gamma plus ZP plus VP square by 2G. This is here at this point, point P, plus H1, where H1 is the head losses that will occur as the liquid or the water moves from point 1 to this point P. Clear? So in this topic, what we will do is that we will neglect the minor losses. This is an assumption. We will neglect the minor losses and we will neglect the velocity head. That's why you can see here, because we are assuming that the pipe lengths are sufficiently long, that we neglect the velocity heads. So then in that case, that's why you see here the energy line and the hydraulic grade line, they are shown as same. So this is assumption, clear? It is written in the textbook. This is our assumption. And minor losses we neglect. So then in that case, we only consider this total head loss here. This will be only equal to the major head loss. So that will be equal to HF. And we will take both this as equal to H. So that's why it is written here H1 and H2 and H3. Clear? So that's why for this point 1 and point B, we have this pipe 1 connected. So that's why it is written here as H1. Now when you simplify, so you can see that this is our assumption. We assume that pipe lengths are sufficiently long, that minor losses and velocity heads are neglected. So now this P by gamma, this is 0, Z1 above a datum, so this is equal to E1 here, and V1 square by 2G. This velocity here is negligible, very small. So this is 0 here, and then at this point again, this is open. So we can see that this is equal to 0. Now the elevation of this point P above a datum, it is represented by EP. So that's why this comes here as EP. And again here the velocity, that is taken as equal to 0. And this H1 comes here. So when we apply the energy equation, we get this relationship, that E1 is equal to EP plus H1. And this is what you can see here in this diagram. This is E1 here. You see here, this is E1. This is what is shown here, E1. And this E1 is equal to this EP. This is here EP. And this is H1. So you can see here, this one. Here, you can see EP is equal to EP plus H1 is equal to E1. Clear? So E1 is equal to H1 plus EP. And this is how it comes, by apply the energy equation between the 2 points here. So similarly, if we apply the energy equation between point P and we consider another point 2 here. This is, let's say, point 2 here. So what we will get? We will get EP equal to E2 plus H2. Now in this case, what will happen? That this is E2. This is E2. Clear? You can see here, this is EP. Sorry, this is EP. So this EP is equal to H2 plus E2. This is the relationship that we will get. EP is equal to E2 plus H2. And if you apply the energy equation between point P and you consider another point here, 3 point here, this is now point 3. So then in that case, we will get that EP, this is equal to E3 plus H3. You can see here this EP, this is equal to H3 plus E3. So E3 plus H3, you can see here this is equal to EP. So EP is equal to E3 plus H3. Next we have case B. So in case B, we are assuming that EP is less than E2. Clear? Now in the previous case, we assume that EP is greater than E2. But now in this case, you can see that EP, this is our EP, and this EP is less than, this is EP. Clear? This is EP. And you can see this is E2. So now in this case, EP is less than E2. So what will happen? When this EP, which is shown here, clear? Here in this piezometer, here we have this water EP. When it is less than E2, so what will happen, that the water will move out of reservoir B. You can see here that Q2 is now out of reservoir. Similarly, this P is lower than A. So what we have, that Q1, it is out of the reservoir A. Clear? But it is above C. So that's why Q3, it is into reservoir C. So now in this case, the continuity equation is that Q1 plus Q2 is equal to Q3. Now applying the energy equation between the surface reservoir A and point P, in this case, now again we consider here one point, and also we consider this point P here. So again, if we apply the energy equation, then in that case, we will have P1 by gamma plus Z1 plus V1 square by 2G is equal to PP by gamma plus ZP plus VP square by 2G plus H1. So again, if you apply here, P by gamma, it is 0, Z1. So this will be equal to E1, and the velocity is 0. So in here, PP by gamma, this is 0, and ZP is taken as equal to EP, and VP square by 2G, that is 0, and the head loss, that is represented by H1. So it comes here. When you simplify, so we get E1 is equal to EP plus H1. Similarly, if you proceed, so in this case, we will have E2 equal to EP plus H2. Now you can see here that H2, you can see in this case, what we have this H2, E2 here. This is E2 from here to here, and then this will be equal to H2, H2. This is H2, and then this is EP. Clear? So what we can see here, EP plus H2 is equal to E2. This is what we get. You will get the same result when you apply the energy equation between P and you consider point 2 here, surface of reservoir B. Yeah. Similarly, when you apply the energy equation between point P and you consider a third point here, point 3 here, so then in that case, EP is equal to E3 plus H3. You can see here EP, clear? This is EP here. This is EP. This is EP. So this is equal to H3, this H3, and then E3. So EP is equal to E3 plus H3. Now, what is the basic difference between case A and case B? If you consider case A, so now we have E1 equal to EP plus H1. This is also the case in case B. EP is equal to E3 plus H3. This is also the case in case B. Clear? Case A and case B, these are common. When we have EP greater than E2, then in that case EP equal to E2 plus H2. But in case B, E2 is equal to EP plus H2. This is the difference between the two cases. This is the same for case A and case B. This is the same for case A and case B. The only difference is here. Clear? So in terms of case A, what is the difference now between case A? So in case A, what was the situation? That EP greater than E2. Clear? So in that case, what we will write down? We will write down that EP is equal to E2 plus H2. This was the situation. EP equal to E2 plus H2. Clear? So what you can see here, EP is equal to H2 plus E2 when EP is greater than E2. And this was case B. So in case B, what is the situation? We have EP less than E2. We have EP less than E2. And in this case, what we have? We have E2 is equal to so this is basically the difference between the two cases. So it means that EP is between surface reservoir A and between the surface reservoir C in both the cases. But in case A, it is above the reservoir surface B, and in the second case it is below the reservoir B surface. Clear? So this is essentially the difference between the two cases. So when we solve the problems, then you have to consider these conditions while solving the problems. Now this diagram, it suggests several different problems. We can have different problems or cases, three of which will be discussed. So there can be different cases when we consider this arrangement for branching pipes. So three cases we will discuss. They are discussed in your textbook. So first is case 1. For what is the case 1? Find the flow to or from two reservoirs and the surface elevation of one of these, given the other flow and two elevations and all the pipe data. What it means? That E1, for example, E1 and E2 are given. All the other pipe lengths and diameters will be given, and Q1 or Q2 will be given. So it means that if the elevation of the water surface in the two reservoirs is given, then the discharge for one of them is given. Q1 is given or Q2 is given. This is case 1 problem, and it will be required to calculate the elevation of the third reservoir. So this is case 1. What is case 1? Case 1 is that we are given two reservoir elevations and discharge for one of them. For example, E1 is given and E2 given. Discharge for one of them is given. In the question, either Q1 will be given or Q2 will be given. So this will be the given data, and it will be required to calculate the elevation of the water surface in the third reservoir. This is case 1. So if case 1 is given, how we will proceed to solve the problem for case 1? So in this case, let us assume that Q1 is given. Clear? E1, in this case, what we are assuming, that E1 is given, E2 is given, and let's say Q1 is given. It can be Q2 given, but either Q1 given or Q2 given, one of them will be given to us. So let us assume that Q1 is given. So how we proceed to solve the problem? You will calculate Q1 divided by A1 in order to get V1. Then H1 is given by, which is the major head loss, is given by the Darcy-Weisbach equation. F1 L1 by D1 V1 square by 2G. So now in this case, we need to calculate H1. So in here, clear, V1 you put from here. This length and diameter, these are given. Now from where F1 will come? This is the friction factor. So you will use Moody's chart or Holland equation to find proper value of F, this friction factor. Clear? So now you have V1, D1 is given. So for the fluid property, you can calculate the Reynolds number. You can calculate the Reynolds number, which is given as V into the diameter D divided by nu. Clear? Kinematic viscosity. So you can easily calculate the R, and then you can calculate E by D. The material property will be given to us. Clear? And the discharge, here it is given for pipe 1, so we can calculate V1. For that V1 you put here, D1 by fluid property, kinematic viscosity, you can calculate the Reynolds number, and then E, which is the absolute roughness, that will be given. The pipe material will be known to us, so we can calculate E by D, and then using this, either you go to Moody chart or use Holland equation, you can easily calculate the value of F. This we can calculate, and that you can put here in order to calculate H1. So now E1 is known to us, H1 you calculate from here, this you put here, so we can easily calculate EP. Now E2 is also given to us, so when you calculate EP, we can now easily calculate H2 according to case A or case B that we discuss. Clear? So now we calculate EP and E2 is given. So what you can do, according to case A and case B that we discuss, we can calculate H2. For example, I go back. here. You can see here case A or case B. So if EP is greater than E2, use this equation. If EP is less than E2, use this equation. Clear? So we can calculate H2. Then you can calculate Q2. Clear? How to calculate Q2? We will assume turbulent flow. This will be the assumption that let turbulent flow occur in the pipe. So this is the equation that we already discussed before. Clear? That you can calculate the discharge. Q is equal to AV, and this V is given by this expression here. If you remember, we solved the single pipe flow problems, and there was a trial and error procedure to calculate the F. So in order to avoid the trial and error procedure, if you remember, there was a direct solution. Clear? In the direct solution, we can avoid the trial and error procedure. Clear? We develop this equation. We develop this equation while solving the single pipe flow problems. So there is no F involved here. You can see here. We eliminate F using the Reynolds number and the Darcy-Weisbach formula. Clear? And the Colebrook equation that we use. So comparing those, we come up with this equation for the velocity and multiply by area for the discharge. Now in this case, we directly calculate the discharge, but there is no friction factor. Clear? So this we already discussed and we solved a problem on this. But here the assumption is that we have turbulent flow. Clear? When you calculate Q2, then you can calculate again the Reynolds number by calculating the velocity V2. Clear? From Q2, we can calculate V2, and that you can put here to calculate the Reynolds number, and Reynolds number should be greater than 2000, 4000 to be fully turbulent flow. So that you have to apply a check that yes, the flow is turbulent flow. Then application of this equation will be valid. So now here what we are doing, that we calculate Q2, we assume the flow to be turbulent flow, and we directly calculate from here. Now in this equation, everything is known to us. So this HF, this is H2 in that case here. Similarly, length and diameter, everything is known. This is fluid property, should be known to us. So now Q2 we calculate, and then Q3 can be calculated according to case A or case B. Clear? So when we have case A, what is the relationship? If I go back, you saw that when we have case B, this is the relationship for case B. And if we have case A, then this is the relationship. Clear? In case A, then you can calculate Q3 because Q1 and Q2 are known, and Q3 you can calculate if we have case A. If we have case B, then you can use this relationship to calculate Q3. Clear? This is what it says, that you calculate Q3 according to case A or case B. And then from Q3, we can calculate V3 equal to Q3 by A3. And then this V3 that you can put here in order to calculate H3. Now F3 is unknown. From where F3 will come? So for F3, we use the same concept here. You use Moody chart or Holland equation to calculate F3, because now V3 is known, and then you can proceed like this. Calculate R3 and E by D for the third pipe, and then use Moody chart or Holland equation and calculate F3. Then E3 will be equal to EP. Clear? EP we already calculate here, in here, see? From here. And H3 you calculate here, from here, H3. So you can calculate E3. And this is what was required, that we calculate what was the required for this problem in case 1, E3, that we calculate E3. So when surface elevation for two reservoir is given and discharge for one of them is given, either Q1 given or Q2 given, what will be required? E3. So how we proceed? This is how we proceed to solve that problem. Clear? So this is how you can see in the end we determine E3. So this is case 1 problem. Clear? When we have case 1 problem, then this is the procedure that you will follow when solve the problem. Next we have case 2. So what is case 2? Find the flow to or from two reservoirs and the surface elevation of the third given. The other flow and two elevations and all the pipe data. So find the flow to or from two reservoirs and the surface elevation of the third, given the other flow and two elevations and all the pipe data, means the length and the diameter. So in this case, suppose E1 and E3 given. We are supposing that, let's say, E1 is given and E3 is given. Given all the pipe lengths and diameters, and Q2 is given. So what is required to calculate E2? Now it is required to calculate E2. So this is case 2. What is case 2? That the elevation of the surface reservoir for 2, that will be given, and the discharge for the third will be given. Clear? If E1 is given and E3 is given, then Q2 will be given. What was case 1? That if E1 is given and E3 is given, Q1 or Q3 is given. Discharge for one of them is given. Either Q1 given or Q3 given. This was case 2, case 1. Now what is case 2? That if, for example, E1 is given and E3 is given, then Q2 will be given. Discharge for the third will be given. This is now case 2. And what will be required? It will be required to calculate E2. To calculate this E2, this we have to calculate. So now for case 2, how we will proceed to solve the problem, what steps we should follow in order to solve such type of problem. First, you have to assume the value of EP, because now E1 is given and E3 is given and Q2 is given. This will be given to us. So we don't know that this EP. Clear? So this EP has to be between E1 and E3, because we saw that in all the cases EP, it will be between E1 and E3, but it can be above E2 or it can be below E2. So this is the difference. Clear? So now we don't know that this EP, where is this elevation lies, above this E2 or below this E2, but it must be between E1 and E3. So what we will do, that essentially it is a trial and error procedure. We will assume EP value, then we will find H1 and H3. If you assume the EP value, then we can find H1 and H3 from this expression that we already discussed. H1 will be equal to E1 minus EP. Clear? And H3 will be equal to EP minus E3. This equation that we discussed while discussing case A and B earlier. So using that expressions that we apply the energy equation between the points. So when EP is known, clear, then H1 you can calculate. Clear? So H1 will be equal to E1 minus EP. You see here. And H3, this is H3. This will be equal to EP minus E3. Then we have to calculate Q1 and Q3. So we will assume turbulent flow. And how to calculate? We apply this equation that we discussed previously. In this case, to calculate Q1 and Q3, H1 and H3, you can put here. You see HF. So this H1, you can put here and here also. All other things are known. You will calculate Q1. Then you can put this H3 here and also here, and then we can calculate Q3. But here the assumption is that we are assuming the flows to be turbulent flows. So it means that these discharges will be only correct if the flows are turbulent. And how to prove that? When the discharges are known, you can calculate the velocity. And from the velocity, we can calculate the Reynolds number. And then from the Reynolds number and the relative roughness, E by D, using Moody's chart or Haaland equation, you can calculate the friction factor. But from the Reynolds number, it will already tell you that the flow is turbulent or not. Clear? If these do not satisfy discharge relations at J, then we must adjust EP until they do so. What it means? That what is given in this case? In this case, Q2 is given. So now what we did essentially in the steps is that we calculated Q1 and Q3. So now what we will do is that we will apply the continuity at this junction J. At this point, we will apply the continuity. So we have case A or case B. Then in that case, it will be equal to Q1 plus minus Q2 equal to Q3. Because we discusses the two cases, that either we have Q1 equal to Q2 plus Q3, or in the second case what we have is that Q1 plus Q2 is equal to Q3. So now Q2 is given, Q1 and Q3 you calculate. So according to this, we have to satisfy the discharge equation. Clear? If the discharge equation is not satisfied, then you have to change the value of EP, unless and until, adjust EP unless and until that the continuity equation is satisfied. So that is why it is a trial and error procedure, because this will be the first assumption, that we assume the value for EP. If the discharge equation is not satisfied, then in that case we have to go for the second trial and so on, unless and until that the discharge equation is satisfied. So once the discharge equation is satisfied, then we can calculate V2, because Q2 is given to us, and then from there we can calculate R2. From V2 we can calculate R2 and F2, as I said earlier. So in that case, R2 is the Reynolds number and F2 is the friction factor, because from V2 you calculate R2, and then from R2 and E by D for pipe 2, as I explained, you can calculate F2 from Moody's chart or Holland equation, and this F2 you can put here to calculate H2. V2 is already calculated from Q2, this one here. And then E2 will be equal to EP plus minus H2. Plus minus because we have two cases, as you saw here, case A and case B. So that's why accordingly then E2 will be equal to EP plus minus H2. So what was required in this case? If I go back to the problem, so this was required to calculate E2, the elevation of the water surface in the reservoir B. So these are the steps how you will proceed to calculate E2. This is what was required to calculate. Clear? Now in this case, as I said, that essentially we have a trial and error procedure. So we will have trial and error because we don't know first exactly the position of EP. If initially we can guess the correct position of EP, then in the first trial we will get the solution. Clear? Because we have to justify this condition here. So in this case Q2 is given, but Q1 and Q3 comes because we assume the value of this EP. So we don't know the value of EP. If we by chance we know the exact value and correct value of EP, then we can correctly calculate Q1, Q3, and it will automatically satisfy this equation. But since this equation may not be satisfied because we are assuming a p-value, so we will go for the second trial, for the third trial, and so on, unless and until the continuity is satisfied. So this is a trial and error procedure. Clear? So in order to simplify this trial and error procedure, this figure given in our textbook can help us. So what this figure represents, it has summation of q here, shown here on the x-axis, summation of q. And what is summation of q? We already discussed that summation of q is just the sum of flows at this point here, at the junction point. So summation of q at j, point j, it is simply equal to inflows, whatever the flows that moves towards, inflows minus outflows. This is summation of qj. So the inflows that is coming to this junction j, and the outflows. For example, in this diagram, what is the inflow? Inflow is q1. So in this diagram, according to this diagram here, this qj, this is equal to what? Inflows. What is the inflow? q1. Then we have minus. What are the outflows? So the outflow is q2 and q3. So this will be equal to q2 plus q3. This is summation of qj. So that summation of qj that you plot here, this is what you see here along the x-axis. So it can be plus, it can be minus. If inflows are more, clear, and outflows are less, it will be plus. But if outflows are more, inflows are less, then it will be minus. So this is how you do. For example, in trial 1, you have this point here, and this is the vertical axis represents elevation of P. Clear? And at this point P, this is point P, the elevation of P value, for which you can see here for this P, summation of Q is 0. So this is the required condition, because for this P value, summation of Q is 0. It means inflows minus outflows is equal to 0. And this is the required condition. What is the required condition? That sum of inflows minus sum of outflows should be equal to 0. Clear? So it will only happen for this P elevation here. But this P elevation we don't know in advance. If we know this P value, so this P value we can assume here. This will be the correct P value, and we will just get the solution in one trial. But since we don't know, so what we do is that we assume, let's say this was your first value, then this was your second value, and so on. You get a third value, and so on. So using this diagram, we get a help. So when we join these trial values by a line, it will not be a straight line, but we assume a straight line. Clear? So then using this figure, we can calculate this value of P by interpolation. So for this value of P, the continuity equation will be satisfied, and we can easily find the final solution to the problem. So this is essentially a trial and error procedure for case 2, because we don't know the correct value of EP. It will be a trial and error procedure, but to help converge the value of EP to the correct value, this figure plotted here, through this figure, we can use interpolation to calculate the P value, which will satisfy the continuity equation. This is the requirement. And we can easily find the final solution. Otherwise, you will just increase and decrease the value of EP unless and until the continuity equation is satisfied. So it may take more number of trials. Clear? But with the help of this diagram, we can easily get the correct value of P, but for that, you have to do more than one trial, minimum 2 trial or 3 trial. Only then we can use this concept to do the find the correct value by using interpolation, and then we can find the final solution to this problem. Clear?